Hello all, welcome back to operating system course. So in the last class we had studied about SJF algorithm. So today we will be looking into priority algorithm, okay, priority scheduling. So in the priority algorithm what will happen is each process will be having burst time. Along with the burst time it would be having priority assigned to it. Okay. Now this priority it can be either internal or it can be defined externally as well. So, priority of the process when it is defined internally, it can be, decided based on the memory requirements, time limits, number of open files, then the ratio of input output to your CPU burst, etc. But whenever it is defined, when the priority is defined externally, so those are set based on the criteria outside of your operating system, like the importance of the process. Okay, so priority will be based or it can be given to a process either internally or externally. Fine. So in the priority algorithm, as I said, along with your the process, it has along with your burst time, it would also be having the priority. So the priority is a number. Okay, so basically it would be some fixed range of numbers either from 0 to 7 or from 0 to 4095. It differs. Okay, and in some system what will happen is the low number it represents low priority. In other system what can happen, the low number it can represent high priority. If suppose I'll give you example, like you have process P1 and P2, the burst time is 5 for process P1 and 2 for process P2. Fine. Apart from this, you will also be having priority, something like this 1 and 2. Fine. So, in some system, what happens is whenever you have the low numbers or priority, wherever you have the low numbers, so these low number, that is the lowest number in the priority column. So the lowest number it can represent the high priority process, or in some systems what can happen is this low number it can represent low priority. This would be specified in the problem. Okay, and so how do you solve a problem is like, so wherever you have the process with the highest priority, you have to take that first and execute that. Once that execution is done, what you do, you check again the ready queue, the process is in the ready queue, check for the lowest or check for the priority of the process, whichever process has the highest priority, take that one and execute that one. So suppose if you have this condition, okay, let us take this one, like P3 process is there, its burst time is 20 and priority is 2. The condition here is you have two processes with the same priority, right? So in this situation, how will you break the time? So again, you have to apply FCFS. Okay, you have to apply FCFS and choose the one process which has arrived first. Okay, and in the priority scheduling algorithms also, you have two flavors. This priority scheduling, it can be preemptive or it can be non-preemptive. So we will study only non-preemptive priority scheduling. Okay, we'll consider an example. Okay, so wherein we have five processes P1, P2, P3, P4, P5 having the burst time 10, 1, 2, 1 and 5 respectively, along with their priorities. The priority of process P1 is 3, P2 is 1, P3 is 4, then P4 is 5 and P5 is 2. Okay, so just now we had discussed, right? We will assume here that, okay, first thing we are considering only non-preemptive scheduling type of priority algorithm. Okay, that means once the CPU has been given to the process, that process would be executed fully, and upon completion only the CPU would be given to the next process. Okay, so again we will assume all the processes have arrived at the time 0 and in this order P1, P2, P3, P4, P5. Fine. So first thing, in the priority scheduling, check for the priority of the process. So we will consider, as you can see here in the problem, it is not given like whether one is of higher priority or lower priority. So in this case, whenever it is not specifically mentioned in the problem, that is which number it represents high priority. So we will just assume that the lowest number it represents the higher priority. So in our case, the assumption is 1. Priority 1 means it is of higher priority. Okay, wherever the process has the priority 1, that means it has the highest importance. So while drawing your Gantt chart, consider the process which has the highest priority. In our case, 1 is of highest priority. That means the process 2 has to be represented in the Gantt chart first. Okay, as we have assumed all the process have arrived at time 0, that's why 0 is written over here. We represent P2 here, and now check for the burst time. How much millisecond your P2 requires? It requires 1 millisecond, right? 0 plus 1 is 1 here. Okay, next, this is done. Now check the priority of other processes. 1 is done. Do we have any other ones here? No. What is the next number? 2. Now you have to take that process which has the priority 2. Okay. So which process has the priority 2? It is P5. Now take the P5 and assign it to the CPU. That means in the Gantt chart represent P5 next. Then add up the burst time. It requires 5 milliseconds, right? 1 plus 5, you have 6 over here. Now this is done. Compare the priority now. 3, 4, 5 you have, right? Which is the smallest? 3 is the smallest, right? So we will consider P1 now. Okay. So we will represent P1 here. 6 plus the burst time 10. It is 16 over here. This is done. Now you have 4 and 5 priority. So 4 is smallest, right? Represent P3, which requires 2 milliseconds. So 16 plus 2 is 18. This is done. And the last process is P4. Represent it, and it needs only 1 millisecond, right? 18 plus 1 is 19. Fine. This is also done. You can cross verify whether it is the burst time calculation, it is giving up 19 milliseconds or not. Okay. The next thing what you have to do, you have to have the waiting time for all the processes. So for all the process P1 to P5, check for the waiting time. So first we have written P1. What is how many millisecond P1 has waited? It has waited 6 milliseconds. Write that. P2, check for it. It has waited for 0 millisecond. P3, it has waited 16 millisecond here. P4, it is 18 milliseconds, and P5, it is 1 millisecond. Okay. So calculate the average waiting time. Sum up all these things and divided by 5. That is total number of process. You are getting 8.2 milliseconds. Okay. Now we will calculate the turnaround time for this one. Let me just clear this out. Okay. So I'll write here turnaround time for all the process P1, P2, P3, P4 and P5. Okay. Okay. What is the turnaround time for P1? Completion time, it is here 16 milliseconds. Okay. Then P2, it is 1 millisecond. P3, it is 18. P4, it is 19 millisecond. And P5, it is 6 milliseconds. Right? Now calculate. Okay, this is average turnaround time. Add up all these things. 16 plus 1 plus 18 plus 19 plus 6. It is 60 divided by total number of the process, which is 5. That is 12 milliseconds. Okay. So this is how you have to draw the Gantt chart, calculate waiting time, average waiting time, turnaround time and average turnaround time. Now put up the formula and check whether you have correct or the waiting time and turnaround time is right or wrong. So first we'll calculate the turnaround time. The formula is completion time minus arrival time. Completion time is, you can see here, we have written completion time already. Arrival time for all the process is 0. So if you minus 0 from all these things, it will remain as is, right? We will calculate waiting time now. Waiting time is equal to turnaround time minus your burst time. Okay, so turnaround time of process P1 is 16 minus burst time is 10. 16 minus 10, you have got 6 milliseconds. P2 1 minus burst time is 1. 1 minus 1 0. P3 18 milliseconds minus the burst time 2, that means 16 milliseconds. P4 19 minus 1 is the burst time, that means 18. Last one is 6 milliseconds for P5 and burst time is 5. 6 minus 1 is 6 minus 5 is 1. Yeah, it is 1 millisecond over here. Okay, average waiting time remains as is. There are some problems with this priority algorithm. So the problem here is there might be a chances of indefinite blocking, or that we call it as starvation. Okay, let me write here. The problem is starvation. Okay, indefinite blocking or starvation. So when do we say that the process is blocked? So whenever the process is ready to run but it is waiting for the CPU, but the CPU has been given to another process which is using it, right? That time we say that the process is blocked. But in the priority scheduling, if any new process it enters the ready queue with the priority, it is higher than that of the process that are already in your ready queue. With the ready queue has lower priority process. So in this case, what will happen? The lower priority process they have to wait, right, till your higher priority process it completes execution. Say for example, in our situation only, say suppose let us take this one. Okay, here till P1 it is okay. P1 is executing. Okay, still you have P3 and P4 having the priority 4 and 5 in the ready queue. But say suppose there comes another process P6 having the priority 1 again. In this case, what will happen? P3 and P4 will have to wait again. Then the CPU would be given to this particular P6 process, right? So that's why we call this starvation here. That is, whenever the higher priority process enters into the ready queue, the lower priority process, which are already in the ready queue and waiting for the CPU, they have to wait. So how can we prevent this starvation? So we have a method or technique called as aging. Okay, fine. So to prevent starvation, we have a technique called as aging. So, what do you mean by aging then? So, in aging technique, what we do is we keep increasing the priority of low priority process based on its waiting time. Say, for example, say if we decide aging factor to be zero point 0.5 for each day of waiting. Okay, say if you have a process with priority 20 which comes into the ready queue. Priority 20 means lowest priority. Okay, so that comes into the ready queue. So what will happen? So that process which is having the lower priority, that is 20, it would be kept in the ready queue, right? Why? Because higher priority processes are coming into the ready queue and they are getting executed. So with this aging technique, what we can do is like we can increase the priority of that particular process. Say you have a process with the priority 20 and it has entered the ready queue. In the aging technique, what we do, we assign some factor. Okay, so this is called as aging factor. This is nothing but you keep on adding this zero point 0.5 or not adding, decreasing zero point 0.5 to your process priority. Okay, that means suppose your process has waited for 1 day in the ready queue. What will happen the next day? Its priority would be reduced by zero point 0.5 from 20. Next day it would be reduced to 19.5. Likewise, day by day zero point 0.5 would be decreased from its priority, and 1 day what will happen? It would be the highest priority process and that would be taken for execution. So we have removed that indefinite blocking of the process here. Okay, so we will see another problem in the next video.